In the last video we looked at sine, cos and tan graphs, and we looked at their period and their amplitude. We are now going to look at what happens when you adapt those graphs, because we said they're useful in sound production, but in order to give you a really visual image, we are going to be looking at them in a much more literal wave form. So here we've got a classic wave, and we're just going to say it's sine x. What can we do to it? Well, imagine what happens on the sea. We've got lots of different options. One option that might occur is that perhaps it's a stormy day. So your waves are going higher than they were before. Nothing's changing, but your waves are now twice the height they were before. And some of the fish are getting caught in the open air. So what's happened here? We've had a stormy day and our amplitude has changed. Now, how could we show this effect in our formula? Well, if before we were going between -1 and 1, and now we're going between -2 and 2, we can show this in our expression as y equals 2 sine x. Everything is going to be twice the height. So if your normal sine graph, instead of being between 1 and -1, it's between 2 and -2. So that's one option. We can have a stormy day. Let's have a look at the other options. Well, what about if it's 6 hours later? What could happen? So it's 6 hours later. Our tides come in and out every 6 hours. And again, apart from me not being an incredible drawer, that is the same wave. It's just as many of them fit in. It's the same height, same amplitude, and it starts at the same place. So this is the same wave, but it's now low tide. How could we show in our formula that we have moved down? And by how far have we moved down here? Normally we go between 1, 0 and -1. Here we're between -1. That would be -2 because it has to be the same distance. And -3. So every point has gone down by 2. Down by 2. Down by 2. The way we show this is we would subtract 2 from our sine x. It's our normal sine x graph minus 2 on every point. We've looked at how our waves can be affected due to the weather, so stormy weather, bigger waves, and how they can be affected due to the time of day in terms of the tides. But there's other things that can happen. For example, we can have more or less waves in the same amount of time. So I'll just sketch this. Now, the waves are still the same height, but now we've got more of them. And the question is, how many more, and how does it change our formula? So our original wave, we have 1 sine wave, 2 sine wave, 3 sine waves, and we have a half there as well. So we end up with 3.5 sine waves. Now, if we look at the purple ones, how many purple sine waves do we have? 1, 2, 3, 4, 5, 6, 7. So we have twice as many sine waves in the same space. And the way this affects our formula is we put a little 2 in front of the x. It's affecting the x-axis, so what you'll often see is brackets around the 2x to let you know which variable the 2 is affecting. Now that 2 also gives us some really valuable information. So we know that normally a sine wave has a period of 360. To find the period of the purple wave or the dark blue wave, all we have to do is take 360 and divide it by 2. And it makes sense because if one wave takes 360 and you have 2 waves in that space, then each of those needs to be 180. There was one more type of, one final way we can manipulate these graphs. And similarly to the y-axis, where you can affect the amplitude and you can also shift it, we also are able to do changing the frequency and shift the graph right or left. But we want an example that we can visualize this with. Now, if a boat goes past you and the waves start here at 0 seconds, you're going to have a sine wave that goes off from you and eventually knocks into other boats. But the boat didn't pass you at 0 seconds. The boat actually passed you at 180 seconds. So it passed 2 minutes later. Now let's visualize what happens here. Well, our wave would still start in the same place, but it would be almost an exact mirror image of the sine wave you started with. So everything that happened at 0 seconds would now happen at 180 seconds. Everything that happened at 90 seconds would now happen at 270. Anything at 270 would now be at 450. So everything is delayed. Now there's something counterintuitive about this in that you've moved along the positive axis in the right direction. For this to be shown in your formula, in your expression, however, it's take away 180. And those brackets, remember, mean that we are affecting the x values. If you didn't have those brackets there, people would think your graph had just been shifted downwards 180. Now, this is further explained in the notes with a little example. But all you need to remember is if you move to the right, it's negative. If your graph moves to the left, it's positive, and you're adding on to your x value. To recap the 4 different ways we can visualize our waves being affected. They can be altered in size, in magnitude, by a value at the front, which we call A. They can also be altered at the end, and that would change their height. So you'd still have the same size, but it would be shifted up or down. You can change the frequency. You can change how many of them there are in a space, and that goes in front of the x, or you can shift where your wave starts. And these are the 4 different things you can do that would still leave you with a sine wave.